Welcome back to Stat 218. What we're doing today is diving in on Chapter 10, chi-square, but only to assess relationships. The last section in Chapter 9 was chi-square, but for the purpose of measuring goodness of fit. The way to think about the difference is if you have just a collection of categories that the data may fall into. For example, you might roll a 1 or a 2 or a 3, a 4, a 5, or a 6 on a die. You're maybe counting how many 1s, how many 2s, how many 3s, 4s, 5s, and 6s, just to see if you get 1/6 of each of the varieties. In Chapter 10, we're assessing possible relationships between explanatory and response variables in the context of where we're sort of seeing things work out in our table. And again, this is something to sort of maybe have written down for the final exam. In Chapter 10 here, we've got an explanatory variable that's 2 or 3 different levels, and our response variable is categorical nature. It's going to be a Chapter 10 approach that we'll be utilizing. So here's the example continued a little bit. We've looked at these data before, but the data are essentially from an experiment that got the medicine Xenical approved by the FDA for usage for weight loss. Now, when you ever get a drug approved by the FDA, one of the bits of data you are required to submit is information about possible side effects, and Xenical being an orlistat, essentially a little chunk of plastic that binds to a glob of fat inside the stomach wall or inside the stomach, and then between the little chunk of plastic and then the fat cell, it's too big to be absorbed through the stomach wall into the bloodstream. You'd expect that maybe there's going to be extra fat in a person's GI tract, and it's going to just pass right through, or as the commercial says, eliminated via natural process. So they considered the question of, will there be, quote, explosive diarrhea, unquote, in people who are taking Xenical at a higher rate. Now, in the way they reported it, they described the condition as fecal urgency. Euphemisms, you know, you got to run with them. But no one who's participating in the study is going to be expected to know the term fecal urgency, what it medically means. And so they simply asked people, have you had explosive diarrhea at any point in time in the last 3 months since beginning the medication? Now, because it was a randomized controlled double-blind study, no one knew whether they're in the treatment group or the control group. But here are the data. 1913 individuals taking Xenical, 356 experienced fecal urgency. 1466 in the placebo taking control group, and 98 experienced fecal urgency. So if this were a regular class, I'd probably stop and pause and ask, is there a relationship? And students would toss up answers like yes and no. Yes, people tended to say 356 of 2,000 is a higher rate than 100 of 1,500. And so they'd say it looks as though there might be a relationship. And I think that makes sense. How could we pursue that? Well, with the hypothesis test, we can define 2 different numbers, P1 and P2. I'm defining P1 as the rate of fecal urgency if you're in the Xenical taking group, literally the chance of FU given you're taking Xenical. And I'm going to define P2 as the corresponding rate for the placebo group. You might even think about our data as providing natural estimates of P1 and P2. The rate of fecal urgency of the Xenical taking people would be P1, and P2 is the rate in the second row. The hypotheses that we have are independence, or that there's a relationship. P1 and P2 are the same. In other words, whether you take Xenical or not, the rate of fecal urgency is the same. That's our null hypothesis. The alternative is that the rates are different between the 2 groups, P1 and P2. They differ from each other. Okay, so to develop some thoughts about it, the rate of P1 in our sample, Okay, I'll call P1 hat. It's 356 of the 1913, 18.6%. P2 hat is 98 of the 1466, or 6.7%. It looks as though it's almost 3 times higher, the rate in the first row than the second row. The rate of FU in the Xenical taking group is maybe almost 3 times the rate of FU in the placebo taking group. But we need to use a hypothesis test to see if that difference in the rates, that ratio of the rates perhaps, is so great that we're convinced that it's reflecting a true trend. So let me ask you a couple questions, and hopefully the answers will be obvious. And if they're not, each time I ask a question, you'll stop and pause and think it through. So first question, if I flip a fair coin 100 times, how many heads do I expect? Most of you are thinking, oh, 50 of the 100. What if I try an experiment with a very biased coin that comes heads 13.4% of the time? If I tried that experiment exactly 100 times, how many times should I get a heads in the 100? You'd think, hold on a second, 13.4% of 100, I'd expect 13 or 14, maybe 13.4 heads in the 100 trials. What if I tried that experiment 1,913 times? 0.134 times 1913, again 0.134 times 1913 would give me an expected number of heads. So let's go back to the top. If the null hypothesis were true, then the rate of fecal urgency is the same in both groups. P1 and P2 would be the same. Again, if P1 and P2 are the same, then we have 2 separate rows worth of data, both of which provide us estimators of the unknown common rate P. And so I'm thinking let's just combine both groups. We have 1,913 plus 1466, or 3,379 people. Hold on a second, I'm going to pause this recording here. Okay, no, I don't have to. Okay, so we've got 1,913 and then 1466, or 3,379 people. Overall, 356 plus 98, 454 cases of fecal urgency. So the overall rate of fecal urgency is 454 of the 3,379, or 13.4%. Okay, so let's get back down to it. If we take 13.4% of 1913, that would be the expected number of cases of fecal urgency you should be having. Okay, so how do I pull that off? Let's look in terms of, hold on. Okay, I'm sorry, someone just knocked at the door and I lost track of exactly where I was. But I'm sort of thinking that if you were to have a total number of cases of fecal urgency, that's 454 of the 3,379. 454 over 3,379 is 0.134. 13.4% of people. And if in the Xenical taking row, 1913 folks were each experiencing fecal urgency with that rate, 13.4% of 1913, I could write that out as the expected number of cases of fecal urgency in the group that's taking Xenical. So in other words, here's the observed. The expected number of cases would be found by saying 454 over 3,379 times, then that's the rate, times 1913. The row total, 1913, times the column total, 454, over the total of the whole of the table, 3,379. I believe that gives us 257.0. 257.0, 257. is the expected count for that Xenical taking fecal urgency experiencing group. So let's move forward a couple pages in the slides and we'll see where we get to. So, so indeed, for our chi-square, we have to have a collection summing across all the possibilities in our contingency table, all of the contingencies, both rows, both columns, the observed count minus the expected count squared over the expected count, just like in chapter 9, the later sections. The expected counts would be the row sum, in our case 1913, times the sum of the column, 454, over the table sum 3379, 257.0. So we're saying if really Xenical is unrelated to fecal urgency, 257.0 cases of fecal urgency should be those that we would see in that upper left cell. So I always recommend writing out the following. There's the observed table with the actual real data, yay, and then there's a corresponding expected table. And we found, again, 1913, 454, 3379 from the 1913 row total times 454 column total over the total of the table 3379, we get our expected count of 257. And if you expect 257 of the individuals of the 1913 individuals to have had fecal urgency, you would expect the rest would not have had fecal urgency. Literally, the expected counts must sum in the same way that the observed counts sum up. So of the 1913 taking Xenical, you expected 257 to have had fecal urgency. The rest were expected to not. Similarly, 454 cases of fecal urgency, you expected 257 of them from the Xenical taking group. You would expect the rest, 197, from the placebo group. So again, via subtraction, 1466. 1466 is 197 plus something. That something could be found by difference. 1466 minus 197.0 gives us the expected count in the lower right cell. Then all we need to do is to implement our chi-square equation. 357 minus 356 minus 257 squared over 257. The upper left cells first. Then I usually go with upper right cells, lower left, lower right. In my case, I get a chi-square value of 100. And I'm just going to say, you might think that there's 1, 2, 3, 4 categories, so you might think there are 3 degrees of freedom, but no. It happens to be exactly 1 degree of freedom. We'll explain later why. But with 1 degree of freedom, we need to find our chi-square based p-value. So a drag over here in our chi-square table with 1 degree of freedom. Let's pull it up to the top so we can see it. Our chi-square value with 1 degree of freedom of 15.14. Our 101 is even higher than that. So our p-value, our upper tail area, is less than 0.0001. Okay, so what can we conclude? If our p-value is tiny like this, less than 0.0001, I would conclude that there is indeed a relationship, that the rate of fecal urgency is different between our 2 groups, the Xenical taking and the placebo taking groups. Okay, another example. Lost change. A group of students tried to glue a coin to the ground near the campus market on a sunny pair of days. One day it was a quarter, one day it was a 50-cent piece. And they observed whether people were attempting to pick up the coin or not. On the day that there was a quarter glued to the ground, 5 of the 17 attempted to pick it up. And then, excuse me, and then on the day that it was a 50-cent piece, 24 of the 28 attempted to pick up the coin. Let's go through the procedure. I got 17 total attempting to pick up, 17 times the quarter was observed, 28 times. It was a 50-cent piece, 29 tried to pick it up, 16 did not, and there's 45 in total cases. So let's see how we get through this. What would the expected counts be? And I'm going to have the observed over here on the left, and on the right, I'm going to have the expected counts. So the expected count for the upper left is 17, the row total, times then the column total, 29, over the total of the whole of the table, that's 45. So here's where I need to pause my video and do the calculation with my calculator. I'm supposing you all can do that yourself, so you might want to pause and get that done with the calculator before I pick up. So pause now, do the calculation, write down the answer, and see if you get what I got. So here I got 10.96. Now some of you might think, hey, that's pretty close to 11. Could I round it to 11? Always round to 1 or more digits past the decimal mark. I'm usually rounding to 2 digits past the decimal mark. So 10.96 is where I would do my rounding. And I'm thinking if 17 individuals in total saw the quarter and you expected 10.96 of them to have picked it up, again, that's according to the null hypothesis, you'd expect the rest would not have attempted to pick it up, and that's going to be 6.04. Again, 10.96 plus 6.04 gives me the 17. 28. Okay, so 29 down here. I've got 29 cases where someone did attempt to pick it up. I expected 10.96 of them to have been the quarter, so 18.04 here would be the expected count for the quarter, the 50-cent piece picking up. And then I guess 9.04 here. Nope, not 04. 9.96. Okay, so I've got my 1, 2, 3, 4 expected counts, my 4 observed counts. So you might want to take a screenshot or something like that just to refer to later. Maybe I will not eliminate those until I verify that, oh, I got them right there, yay. So I've got my sum of, now, observe my expected squared over expected. I've got the first cell, upper left, 5 minus 10.96 squared over 10.96, and then plus upper right, lower left, and lower right. I've got a chi-square value of 14.66. Again, with our 1 degree of freedom, we could figure out then our p-value, 1 degree of freedom, top row. 14.66 is somewhere in the range from 10.83 to 15.14. So that's where my chi-square value is. My upper tail area is in that range, 0.0001 to 0.001. So 0.001 to 0.001. Upper is less than 0.001, but greater than 0.0001. What about the directionality of my alternative hypothesis? You might have remembered that our alternative is directional. You might also have spotted in the chi-square table that if you have 1 degree of freedom, the directional p-value is half of the table area. So my p-value for my directional tests is the following. 0.005 is less than the p-value, which is less than 0.0005. I'm sorry, 0.000. Needed an extra 2 zeros there. So the p-value is less than triple 0.05, but more than quad 0.05. And so our conclusion would be what? The conclusion would be that we reject the null, believe the alternative hypothesis, that there is a directional relationship that people are more likely to pick up the 50-cent piece than a quarter when seeing a quarter lying on the ground. The rate of attempting to pick it up is less than the rate of picking up a 50-cent piece. Pretty easy. Okay, so skipping over this guy, actually, hold on. Well, I'll talk my way through it, and then we'll show you two other examples where the results are right from a software package. Okay, so do you still smoke after 8 weeks? If you're using a nicotine patch, people who smoke and want to quit smoking would want to know that. And so some of the folks were given a real nicotine patch. Others were given a large Band-Aid with no nicotine in it. 120 people in each of the two categories were tried. 64 were still smoking after 8 weeks. The rest, 56, were not. 160 people were still smoking after 8 weeks in total, and we know that 64 were experiencing the patch, so 96 over here, and then 24. I think I got my numbers right. So fill in the missing values. The null and alternative hypothesis. Well, we have to read the question carefully. What would be the null or alternative hypothesis? Directional or non-directional? Think it through, pause if need be, and ask yourself, directional or non-directional? Well, the null hypothesis always is going to have an equality in it. My null hypothesis is the rate of still smoking with nicotine, N, is equal to the rate of still smoking with the placebo. PP is sort of a strange symbol here, but the rate of still smoking with the nicotine patch and the placebo are the same. The alternative hypothesis also is going to have PN and PP in it, but the alternative hypothesis is that if you have the nicotine patch, the rate of still smoking should be lower. Does it help you quit? If the rate is lower, that says the nicotine patch helps a person quit smoking. If, on the other hand, we simply say that the rate is not equal to, it says either the nicotine patch helps or it doesn't. What about the expected counts? The expected counts, I'm going to say you should check your math. Actually, you should check my math. I'm going to fill in my expected counts, but you should stop and pause first before you move forward. Okay, now that you've paused because you found the answers, I got 80-40, 80-40. You should have as well. For the upper left cell, here's your hint. Row total 120 times the column total 160 over the total of the whole of the table 240. And I note 120 over 240 is just half of 160. That's how I got the 80 in the upper left cell. Chi-square, again, stop and pause. Here's your equation. Chi-square is the observed minus the expected squared over the expected. The first term is 64 minus 80 squared over 80. The second term is 56 minus 40 squared over 40. And then I have two additional terms, and I got 19.2. Did y'all get 19.2? I'm actually not sure that I got 19.2. It's either 19.2 or 19.8 if I remember from a past class, but is that result statistically significant? The answer is yes, because our p-value is well below 0.05. It's less than 0.0001. Okay. So let's see where we get to with 2 additional examples. I want to do those 2 additional examples, and one of them is with data on the Donner Party. The Donner Party, you remember the story if you took California history. There's 2 types of individuals that went out on the trip. There's the females and the males. These are all the data from people aged 13 and up who were on the journey. Survival in blue, died in red. It looks as though the rate of survival is smaller in the men than in the women, okay? 2/3 and 1/3, something like that. If we express this in a tabular form, 5 dead females of the 15 females for a 1/3 dead rate, 2/3 survival rate. In the males, there's 30 males, 10 survived, 1/3 survived, 2/3 died, 20 of the 30 died, 2/3. We've got the counts, 5, 10, 20, 10. Then the rates are chi-square value. It's always the Pearson chi-square value in our class. And it's a 0.0039. Null hypothesis of equality of survival rates is rejected because my p-value is below alpha 0.05. Good place to stop for the day. So, or for this video, enjoy, and we'll talk to you in the future.